So in this lecture video, we will discuss our last topic, that is constraint and nonlinear programming problem, nonlinear optimization constraint, nonlinear optimization using how to solve that using conductor conditions. Solution. Okay, solution. Okay, solution of a constraint nonlinear programming problem by conductor conditions. So before that, you have to understand what is the constrained nonlinear optimization technique. Okay, that you might have known from the previous classes, and we will, before getting into this solution using conductor conditions, we have the standard form of constrained nonlinear programming problem. It is standard form of a constrained nonlinear programming problem. So the standard form is like this: maximize. It may be maximization problem, that is maximize, or a minimization problem, that is or minimize. Z, okay, Z is equal to Z or F, anything you can take. So Z is equal to F. I'm taking Z. So F of x1, x2, etc. xn. And this subject to the constraints G1, G2, G3, etc. Gm are our constraints. So G1 of x1, x2, etc. xn is less than or equal to P1. So we have been regularly using these notations, so you need not to explain it. So G2 of x1, sorry, x1, x2, etc. xn is then or equal to B2. So like that, we have m constraints, that is Gm of x1, x2, etc. xn is then or equal to Vm. So this is our standard form of constraint optimization problem. Now, how to apply the conductor conditions in this nonlinear constrained nonlinear programming problem. So the steps are So the steps for the solution of a constrained NLPPP by conductor conditions, that are steps. Step 1 is you have to write the nonlinear programming problem. Okay, but to write So the first step, you have to write the given constrained nonlinear programming problem in standard form if it is not in the standard form. Then so this is our first step. Okay, then the standard form means all the objective function, it may be either maximization form or minimization form, but all the constraints g1 g2 g3 etc gm must be in less than or equal to type. So if it is greater than or equal to, then what you have to do is you have to just multiply with -1 on both sides of the inequality. Okay, so that is our first step. Then the second step is uh, convert convert all the less than or equal type constraints into equations which is having equal to sign, okay, by adding slack variables. So slack variables means we have added slack variables, we have introduced the slack variables as s1. My notation is s1, okay, s1 s2 s3 s1 s2 s3 etc up to sm, because we have m number of constraints. Then if it is, you have to add the slack variables which is non-negative, that is either 0 or positive. So you have to square it, s1 square s2 square s3 square, so that it will be a non-negative number. So that is what we are adding this s1 square s2 square. So I'm notating this new constraints. Okay, constraints g1 g2 is transformed into our yes capital G1 of x1, G2 of x, G2 of x1 x2 etc x. So these are the notations. So notations are important in general uh, method. Okay, general method, the notations are important. Then we have, okay, so this is our equation. Then what happens to this, what are these g1 of x1 x2 etc xn will become g1 of x1 x2 etc xn minus b1. This is from right hand side, we have that we what right written as when when it is converted into equality, we have written in the LHS side, so that this minus became, so minus b1 minus b2. Then we have the slack variables s1 square s2 square and etc sm square. So this is our capital G1 G2 etc gm. Then the step 3 is you have to introduce a new function which is known as the Lagrangian function. Okay, Lagrangian function capital L. So it is given by, and will be a function of capital L is a function of x1 x2 etc xn, your decision variables, and then slack variables s1 s2 etc sm, and a new variable that is lambda 1 lambda 2 etc lambda m. Okay, then that is defined as L is equal to f of x1 x2 etc xn minus lambda 1 g1 of x1 x2 etc xn minus lambda 2 g2 of x1 x2 etc xn and minus lambda 3 g3 etc etc minus lambda m gm. So this is our Lagrangian function L. Okay, so that is your objective function. You have to take that into consideration, objective function f of x1 x2 minus lambda 1. All the converted constraints are multiplied by lambda 1 lambda 2 lambda 3 etc lambda m, and you have You are adding all those, and you are subtracting from your objective function f of x1 x2 etc etc. So that is what our Lagrangian function. Okay, and the capital X is our is this the vector capital X is set of all x1 x2 etc xn, and we are defining capital S, which is a set of s1 s2 etc sm, and we are defining the lambda, capital lambda, which is another set of lambda 1 lambda 2 etc lambda m. Okay, so that in short the Lagrangian function can be defined as L of L, which is function of x1 x2 etc xm, and s1 s2 etc xm sm, and lambda 1 lambda 2 etc lambda m. In short, you can write L of vector x, then vector s, and vector lambda, or the set x, set s, and set lambda, and that's equal to f of capital X minus lambda 1 g1 of x minus lambda 2 g2 of x etc minus lambda m gm of x. Okay, and the lambda 1 lambda 2 etc lambda m are called Lagrangian multiplies. So in step 3 you have introduced a function which is known as a Lagrangian function. Okay, so then we will apply the Kundaker conditions defined as for maximization problem and minimization problem. We have the Kundaker conditions differently, it is defined. So if it is maximization problem, you have to apply these set of Kundaker conditions, and for minimization problem you have to apply another set of Kundaker conditions. That means the conditions which are defined by a scientist Kundaker, and that has to be satisfied, or that will satisfy by this Lagrangian function, and the entire constraint optimization problem will satisfy these conditions. Okay, so for maximization problem, it is defined as dou L by dou x1, dou L by dou x2, that is partial differentiation with respect to x1 x2 x3 etc will be 0. Okay, this is the first condition that should satisfy, or that will satisfy for a constrained nonlinear optimization problem. And the next is lambda I into gi of x, okay, minus bi equal to 0. So this will satisfy. So in that then we have uh, a b c we have this g, actually g, okay, gi of x less than or equal to bi for sorry for every values ranging from 1 to m. Then lambda I, the Lagrangian multiplier, must be non-negative, that is greater than or equal to 0 for I varying from 1 to m. Okay, and that means you will get a b c and d for set, okay, for a set of equations. Okay, then you solve that for set of equations. Okay, then you will get the optimized solution x star. Okay, and then for minimization problem we have the condition, the similar conditions are here also defined, dou L by dou x1 equal all that are same, but the only condition that differ is lambda I is less than or equal to 0. That means this is either 0 or negative. Okay, so that's the only difference. Then again you will get four set of equations. Okay, set of equations and conditions. Then you again solve the equations or the conditions, then you will get the optimum solution. Okay, x star. So that is the conductor conditions for solving the constrained nonlinear programming problem. Now we will solve an example so that you will understand the conductor conditions clearly. So the problem is like this. Solve the following. Yes, solve the following constrained nonlinear programming problem using conductor conditions. Using conductor conditions. So the problem is like this: maximize z equal to 2x1 minus x1 square plus x2, and subject to the constraints. The constraints are subject to the constraints. G1 is 2x1 plus 3x2 less than or equal to 6. Then 2x1 plus x2 less than or equal to 4. 2x1 plus x2 less than or equal to 4. G2 of x1 x2. Then x1 x2 greater than or equal to 0. Yes, it's greater than or equal to 0. Then the given, if you observe this given problem of this maximization problem is in standard form. Okay, so the standard form is less than all the constraints g1, g2, etc. gm must be less than or equal to type. Okay, so either maximization or minimization, so it is applicable. And also x1 x2, the decision variables must be non-negative, that is greater than or equal to 0. This is our standard form. And so the first step is you can skip that step, and the second step is convert all the less than or equal to type constraints. You have to convert it by adding into equations. You have to convert, and by adding the slack variables. So the slack variables are s1 square, s2 square, etc. So we have two constraints g1 and g2, so we have two slack variables s1 and s2, and the step 2 will be like this. G1 of x, that is g1 of x1 x2, will be equal to 2x1 plus 3x2, okay, minus 6 plus s1 square equal to 0. And similarly we have g2 of x equal to 2x1 plus x2 minus 4 plus s2 square equal to 0. And now in the next step we have to introduce the function Lagrangian function. You have to formulate the Lagrangian function. So the Lagrangian function is a function of x, s and lambda. So L of x, s, lambda you have to formulate. So that will be equal to, you know, that is f of x minus lambda 1 g1 x k minus lambda 2 g2 x. Okay, so this will be equal to, we have L of x as lambda will be equal to 2 k 2x1 minus x1 square. That means your f of x1 square plus x2 minus lambda 1 into minus lambda 1 to 2x1 plus 3x2 minus 6 plus s1 square, and minus lambda 2 into 2x1 plus x2 minus 4 plus s2 square. Now the contact conditions you have to apply. So after the formation of Lagrangian function, how to apply the contact conditions? Okay, so contact conditions for a maximization problem. Since this problem is a maximization problem, you have to apply, you have to choose that contact conditions for maximization problem. So that will be equal to, the first of all, have two decision variables x1 and x2. So we have to two partial differential dou L by dou x1 equal to 0 first, and that implies with respect to x1, if you differentiate, then you will get 2 minus 2x1, then 0, then lambda 1, then minus 2, okay, minus 2 lambda 1, then x2 0, 6 0 0, 2 lambda 1 minus 2 lambda 2 minus 2 lambda 2, that's equal to 0. So then that means 2 minus 2x1 will be equal to 2 lambda 1 plus 2 lambda 2. Okay, this is equation number 1. Okay, so you have this, the first equation number 1. Then we have dou L by dou x2 with respect to x2. Then I will get 1 minus 3 lambda 1 minus lambda 2 equal to 0, and 3 lambda 1 plus lambda 2 equal to 1. So this is equation number 2. Okay, and the condition B is lambda 1 into 2x1 plus 3x2 minus 6 equal to 0, and this is our equation number 3. And we have the second, that is lambda I, here lambda 2 into gi of x, that means the next constraint g2 of x. So that is 2x1 plus x2 minus bi, so minus 4 equal to 0. So this is our fourth equation. Now I'm applying this condition, C condition, that is yi of x less than or equal to bi, sorry, gi of x less than or equal to bi. That means you will get the inequality as 2x1 plus 3x2 less than or equal to 6. This is 5. Now 2x1 plus x2 less than or equal to 4 also, so 6. Then D condition is lambda I for maximization, it is greater than or equal to 0. So lambda 1 greater than or equal to 0, and we have lambda 2 greater than or equal to 0. So this is equation number 6. Now first of all, now I am going to apply the conditions one by one. So lambda 1 greater than or equal to 0 means, so the case 1 will be lambda 1 equal to 0 and lambda 2 equal to 0. So that means equation 1 becomes, if lambda 1 and lambda 2 both are equal to 0, then that means from this D condition, okay, if it is both are 0, we have the case 1, that means that then 1 implies, equation 1 implies 2 minus 2x1 equal to 0 and 2x1 equal to 2 implies x1 equal to 1. So this is a solution. Now yes, lambda 1 and lambda 2 both are equal to 0, then equation 2 becomes, equation 2 becomes 1 not 1 equal to 0, 1 equal to 0, which is not at all possible. Okay, so that the equation 2 is not satisfied, hence lambda 1 equal to 0 and lambda 2 equal to 0 is not a solution, So this kind of solving the problem is known as trial and error method. So this through trial and error method we will solve this. So the case 1 is not possible, so this is, so I'm going for the case 2, that is lambda 1 equal to 0 and lambda 2 not equal to 0, which is some lambda 2 arbitrarily I'm taking lambda 2 equal to lambda 2 itself. So that means equation 1 becomes 2 minus 2x1 equal to 2 lambda 2. So that means x1, 1 minus x1 is equal to lambda 2. Okay, 1 minus x1 is equal to lambda 2. Then I have from 2, equation 2 implies, if you substitute lambda 1 equal to 0, then you will get lambda 2 is equal to 1. Therefore 1 minus x1 is equal to 1, that implies x1 is equal to 0. Okay, and if lambda 2 not equal to 0, if lambda 2 not equal to 0, then the equation 4 implies we have equation 4, 2x1 plus x2 minus 4 equal to 0. 2x1 plus x2 minus 4 equal to 0. So that means 2x1 plus x2 equal to 4. And okay, so this is our equation 4. I will, yes, this lambda 2 not equal to 0, so lambda 1 0, then this 3 is 0, so lambda 2 not equal to 0, then that means 2x1 plus x2 minus 4 is 0. Okay, So we will get s2 x1 plus x2 equal to 4, and we have x1 equal to 0, so that means x2 equal to 4. Okay, and again but if you substitute x1 equal to 0 and x2 equal to 4 in equation number 5, okay, equation number 5, then you will get 2x1 plus 3x2 less than or equal to 6, is 2x1 plus 3x2 less than or equal to 6, 3x2 less than or equal to 6. That means 2 into 0 plus 3 into 4 less than or equal to 6. That is 12 less than or equal to 6, which is violated. Okay, which is the violation. So you cannot have this condition, this case also. Okay, so this is not again the solution. So the case 2 is also ruled out. Case 2 is also ruled out. So we will go to the next case, that is case 3. It will be lambda 1 not equal to 0 and lambda 2 equal to 0. Okay, just the opposite of previous case. Then if lambda 2 equal to 0 is equal to 0, then equation 1 implies we have 2 minus 2x1 equal to 2 lambda 1. That means 1 minus x1 is equal to lambda 1. And the equation 2 implies we have 3 lambda 1 is equal to 1 and lambda 1 is equal to 1 by 3. That means x1 we will get x1 is equal to 2 by 3 you will get. Okay, so if lambda 1 not equal to 0, then 3 becomes 2x1, equation 3, okay, 2x1 plus 3x2 minus 6, 3x2 minus 6 equal to 0. And if you substitute for x1, that is 2 by 3, then you will get the value of x2, and that is equal to x2 will be equal to 14 by 9. 14 by 9. So x1 you got, x1, x2 you got like this. Okay, then yes, then substitute x1, x2, substituting. So you need to again you have to verify whether this x1 x2 solution is will satisfy all the Kandakar conditions. So substitute x1 solution and x2 solution in equation number 5. Okay, equation number 5, that is, so that will be, you will get the, yes, equation number 5. Yes, in this 5 equation, then you will get 2, okay, as 2 into 2 by 3, right, 2 into 2 by 3 plus 3 into 14 by 9, 14 by 9, which is equal to 4 by 3 plus 42 by 9, that's equal to 12 plus 42 by 9, that is 42 plus 10, 50, 54 by 9. Okay, 54 by 9 is 54 by 9, which is less than or equal to 6. Then yes, that is 6. So 6 is less than or equal to 6. this condition is satisfied. Okay, so then substitute the same in B. You will get, that is 2x1, that is you will get lambda 1. Okay, sorry, not in B, in 6, equation number 6. If you substitute, then you will get 2 into is the second constraint, that is 2 into 2. Okay, 2 into 2 by 3 plus 14 by 9, that's equal to 4 by 3 plus 14 by 9 that's equal to 12 plus 14 by 9. So 26 by 9 you will get 26 by 9. So that will be equal to 2.88, which is less than or equal to 4. So this condition is satisfied. So equation 6 is also satisfied. Okay, so the x1, the solution for this case, in this case x1 equal to 2 by 3 and x2 equal to 14 by 9 and lambda 1 equal to 1 by 3 and lambda 2 equal to 0 satisfies all the Kantakar conditions or the 80 conditions. So hence, therefore, this is a feasible solution. This is a feasible solution. But we cannot stop here because we have to check the another case, the another possibility also, that is lambda 1, both lambda 1 and lambda 2 are not equal to 0. That is case 4, that is lambda 1 not equal to 0 and lambda 2 not equal to 0. Okay, then if lambda 1 not equal to 0, lambda 2 not equal to 0, then from equation 3 and equation 4 we have 2x1 plus 3x2 equal to 6. Let it be 7, equation number 7, and 2x1 plus x2 equal to 4, let it be equation number 8. Okay, this is two equations in two unknowns, so you can solve it very easily and you will get x2 is equal to 1 and x1 is equal to 3 by 2. Now again substitute this x1 and x2 in equation 1. We will get the 2 minus 2x2, 2 minus 2 into 3 by 2, that's equal to 2 lambda 1 plus 2 lambda 2. Then that means 2 cancel, so minus 1 you will get. So 2 lambda 1 plus 2 lambda 2 to minus 1. So this is equation number 9. Again, if you substitute in equation number 2, if you substitute for x1 and x2, then you will get 3 lambda 1 plus lambda 2 equal to 1. So this is 10. So if you again you solve, you can solve these two equations, which are two equations in two unknowns. So you will get lambda 1 equal to 3 by 4, which is greater than 0, and lambda 2 is equal to minus 5 by 4 you will get, which is less than 0. Okay, so hence this is lambda is is we got it negative, so this is the violation. This is the violation of kt condition. Okay, kt condition d, kt condition d. Okay, which which describes that lambda I must be non-negative greater than or equal to. Okay, so the case lambda 1 not equal to 0 and lambda 2 not equal to 0 does not give any feasible solution of the problem. Hence the optimum solution will be given by the case 3, in which x1 is we got it as 2 by 3 and x2 we got it as 14 by 9 and lambda 1 we got it as 1 by 3, lambda 2 equal to 0. So you substitute using z, then z maximum value of z is equal to, you will get it as some, you will get some 22 by 9. I think 22 by 9 you will get, so that will be equal to 2.44. So this is our problem solving using conductor conditions. So next you will on the on the background of this, the solving this problem, you can solve any kind of any problem. So I will give you some assignment questions. So with this we have successfully completed the conductor conditions and its problem solving. So this is our last lecture video. And if you have any doubt, you can contact me, and yes, I will give you the assignment questions, okay, later. So thank you.